İyi akşamlar, hoş geldiniz.
İyi akşamlar hocam.
İyi akşamlar hocam.
Merhabalar. Biraz daha arkadaşlarınız gelsin, sonra sunumunuzu paylaşabiliriz. Ehsan, Aysu, Harunisa, Sıddık'a buradalar.
Merhaba hocam.
Merhabalar, iyi akşamlar.
İyi akşamlar hocam.
Şimdi bir isterseniz deneyin, paylaşmayı Harunisa.
Tamam hocam.
Deneme yapalım, bir sıkıntı var mı teknik olarak? Yok, gayet güzel. Tamam.
Geçiş oluyor mu?
Geçiş oldu.
Tamam.
Slaytı gördük. Giriş ve birinci slayt vardı.
Evet.
Tamam. Bakayım. İsterseniz başlayabilirsiniz. Arkadaşlarınız gelirse ben kabul ederim onları. Ben sesimi kısayım, sizi dinleyeyim.
Tamam hocam. Today we are talking about hydrogen and ammonia energy production and the hybrid systems. The presentation consists of 3 parts and 3 articles actually. One is green hydrogen, 3 is green ammonia, and 3rd is ammonia blended hydrogen fuel engines. We begin with green hydrogen, a promising way to the carbon-free society article. Green hydrogen production methods, electrolysis of water, photocatalysis, and biomass. Energy source of green hydrogen production is mainly power and solar energy. Hydrogen has the advantages of being clean, non-polluting, renewable, storable, and versatile. Its reserves are quite abundant when accounted for by the hydrogen element, and its unit calorific value is relatively high. It can easily be seen as a potential energy storage media that could be what is known as the ultimate energy of the 21st century, and it's important to support the energy transition. In view of the different hydrogen production pathways, hydrogen source can be divided into gray hydrogen, blue hydrogen, and green hydrogen. Gray hydrogen mostly results from the industrial byproducts. Its energy source is mainly fossil fuels, and the hydrogen production process accompanied by the production and emission of carbon dioxide. In modification of the gray hydrogen production method, if the byproduct carbon dioxide can be captured, used, or stored, preventing pollution, then the resultant process is termed blue hydrogen production. If it's obtained through renewable energy sources such as wind energy, solar energy, biomass energy, and other green sources, then it's classified as green hydrogen. The electricity in electrolysis process has great potential to be driven by renewable energy and obtained through low carbon or carbon-free methods. Therefore, this technology is considered to be the most promising green hydrogen production technology. The process of producing hydrogen from water electrolysis is mainly composed of 2 half reactions. Hydrogen evaluation reaction in cathode, you can see in the figure, then oxygen evaluation reaction in the anode. The application and research of this technology mainly includes 4 types: alkaline water electrolysis, proton exchange membranes, solid oxide electrolytic cells, solid polymer anion exchange membrane. Let's take a look at these types of technologies and their difference in video.
Hydrogen electrolysis from water is usually undertaken with liquid alkaline or polymer electrolyte membrane electrolyzers. The alkaline electrolyzer works by immersing 2 electrodes in a liquid electrolyte. When a voltage is applied, the product gases are released, in this case, oxygen and hydrogen. However, it does pose some problems. It is unable to make efficient use of intermittent power supplies, meaning it's incompatible with renewables. It also compromises efficiency during storage. To store enough hydrogen for regular use, you would need either a giant tank or an additional compressor. The PEM electrolyzer overcomes some of these issues by using a solid polymer electrolyte, which is the membrane responsible for the conduction of protons, the separation of hydrogen and oxygen, and the electrical insulation of the electrodes. It's able to make use of the fluctuating power supply from renewables and results in pure hydrogen due to the solid structure of the electrolyte. It is easy and more efficient. However, it has a prohibitively high cost due to its required use of gold, iridium, and platinum. Fortunately, a new type of electrolyzer, the anion exchange membrane, or AEM electrolyzer, provides a solution to all of these problems. It uses an alkaline solid polymeric membrane, eliminating the need for rare and expensive noble metal catalysts. The AEM electrolyzer is a simpler and more efficient system that produces directly compressed hydrogen. It's the key technology that enables lower overall costs. The AEM electrolyzer combines the benefits of the PEM electrolyzer with the cost of an alkaline system. It's an important breakthrough which will enable the economical adoption of hydrogen energy storage systems all over the world.
Then look at in detail all of the electrolysis method. First, we begin with alkaline water electrolysis. The AWA technology covers the earliest industrialization time, reliable technology, low cost, and easy operation, but the device occupied a large area. At present, the device for alkaline water electrolysis technology is mainly composed of electrolyzer, electrolyte, diaphragm, cathode, and anode. Diaphragm means membrane. Generally with low working temperature, and the diaphragm is general purpose asbestos, it is necessary to balance the pressure of the cathode and anode during operation to avoid explosion caused by the interpenetration of hydrogen or oxygen. Since the electrolyzer for alkaline water electrolysis is slow to start and requires long response time, we see in the video, the method of increasing the conversion rate can be achieved by increasing the current intensity or reducing the voltage. In AWE technology, the choice of electrodes and the quality of the diaphragm have a decisive influence of the efficiency of hydrogen production. The effect of electrode concentration on the electrolysis efficiency is significant. The development process, asbestos was replaced as diaphragm used in the early stage due to its poor corrosion resistance. The composite diaphragms formed by the cross-linking of high molecular polymers and specific inorganic materials have already been developed. However, they still need to be optimized. Currently, the research of catalysts used in AWE technology is the hot topics: how to construct electrode materials with low cost, excellent performance, and low energy consumption is the focus of further promoting engineering applications. AWE technology has been widely used in industries such as pharmaceuticals, energy storage, and metallurgy. These processes are represented by some research and development institutions. Some country is most important research and developments, such as China, America, Norway, Belgium, and Italy. Proton exchange membranes, PEM. The PEM technology is easy to integrate and has high conversion efficiency, but the cost is very high. Although the catalyst cost is one of the big reasons to lead this technology not to be applied in large scale, while due to the small size of electrolytic cell, it is easy to couple with wind energy and photovoltaics, so this technology is applicable in the future. For PEM technology, the main device is still an electrode cell, but the core part becomes a polymer cation exchange membrane. The cathode and anode catalysts are attached to this membrane, and the bipolar plate is responsible for the connection of multiple membrane electrodes. The advantage of PEM technology is that it can achieve single conductivity of hydrogen ions and thus has higher safety. In addition, the construction of the electrolytic cell is compact and the electrode does not corrode the device. The research focused on the influence of different proton exchange membranes on the performance of the PEM electrolytic cell and the development of new membrane materials. While the development of PEM technology is originated from the needs to US military oxygen generators, because of the problem of the consumption of renewable energy, European and American countries are actively promoting the intervention of PEM process. Relevant agencies can present of level this filed. The China Germany, United States, United Kingdom, and Canada use this PEM technology and develop them. Solid oxide electrolytic cells. The SOE technology is subject to the certain restrictions due to the high temperature as the working condition. The SOE technology requires a high temperature reaction site. The nickel-based porous cermet is used cathode, and the anode is perovskite oxide of rare earth elements, and the electrode layer is usually as an oxygen ion conductor. Due to the high operation temperature, the standard of material for the internal devices are relatively high. SOE technology has the advantage of flexible coupling with renewable energy. Some institutions have carried out the optimization of solid oxide stacks and the design and operation of the high temperature electrolytic cells. For SOE technology, in addition to stability under high temperature conditions, the anode material also needs to have compatibility with the electrolyte material, while the cathode material has excellent conductivity and catalytic activity. This process is represented by some research and development institutions in United States, Germany, France, and China. After a series of research, the current problems need to be solved in this technology is mainly about the poisoning of electrode materials and the high internal resistance in its long-term operations. Solid polymer anion exchange membrane, AEM. AEM technology is still in the research phase in terms of high temperature working conditions. The AEM technology uses an anion exchange membrane with low working temperature, fast startup, and non-corrosive reaction medium. AEM technology, it is only in the laboratory research stage now, and relative breakthroughs and developments await for the innovation of the electrode materials. The operating parameter of technologies, we can see the four technologies, electrolyte membrane, current density, temperature, required temperature, hydrogen purity, relative equipment volume, operating characteristic, mainability, environmental protection, technology maturity. Zaten burada da görebiliyorsunuz AEM ve SOE teknolojilerinde bazı boşluklar var. Çünkü daha research aşamasında oldukları için bu şekilde. Photocatalysis. Water splitting for hydrogen generation. Photocatalysis is a process in which a catalyst absorbs photons to generate high energy electrons and holes and then initiates a redox reaction. In 1972, Fukushima and Honda discovered that photocatalytic water splitting can produce hydrogen on the titanium oxide electrode. This discovery provides a foundation for realizing solar water splitting to produce hydrogen. This process can convert and store solar energy in the form of chemical energy, which is regarded as a promising environmental green hydrogen production technology. Zaten burada da görebiliyorsunuz. Aslında bu fotokatalitik water splitting olayı dediğimiz şey yapay fotosentez anlamına geliyor. Yani bitkilerin yaptığı şeyi yapay olarak bir maddenin yapması anlamına geliyor. Burada da bu madde gördüğünüz gibi hidrojen üretiyor suyun içinde. Korean researchers have developed a catalysis system that can increase efficiency and reduce the cost of hydrogen production. Let's watch this news about how Korean materials scientists develop a new material to produce hydrogen by the photocatalytic method in 2019.
Shining light at the beaker of water creates tiny bubbles. The film-like solid catalyst developed by Korean researchers uses regular light to convert into hydrogen. The catalyst turns black during the reaction and then returns to its original white color, which means it can be reused multiple times.
We observed that hydrogen was created for a period of 48 hours in light. Hydrogen output stayed the same, so we believe the technology can be used for a long time without the catalyst losing performance.
Under good lighting, a gram of the material used in the catalyst can create 30 milligrams of hydrogen per hour. The new catalyst is 50% more efficient than existing systems. And because it's made of copper instead of expensive platinum, it's much more cost-effective. Also, retrieving hydrogen from water using light does not produce any harmful byproducts.
At present, most hydrogen is made through a methane reformation technique. This is energy intensive and generates a lot of byproducts like greenhouse gases. The new technology only produces hydrogen.
Biomass. Using biomass as raw material through gasification, conversion, decarbonization, and separation, the pure hydrogen is obtained finally. Because in two parts of green hydrogen production, the storage and transportation, occupied for a high proportion, which is the main obstacle to the opening of green hydrogen energy in the energy system. Hydrogen production by biomass is expected to be able to overcome the two major problems, storage and transportation problems of green hydrogen sources and hydrogen storage and transportation cost. The roads to obtain high purity hydrogen are shown in figure 3, and this research of the conversion from methane to hydrogen could be found in table 2. You can see the conversion methods from methane to hydrogen, and we see in the figure biomass feedstock kullandığımız yönteme göre enzimatik hidroliz, pre-treatment metodu, gasification metodu veya diğer metotlar, other metotları, anaerobic fermentation metotları kullanarak ve etanol, metanol eklemesi yaparak nasıl hidrojen elde edebileceğimizi gösteren bir figür bu. Gördüğünüz üzere. Devam edelim. Biological hydrogen production and thermochemical hydrogen production are two pathways for the hydrogen production by biomass. Biological ways show hydrogen producing microorganisms such as anaerobic fermentation, hydrogen production, and photosynthetic hydrogen production, but the yield and stability are poor and the possibility of large-scale production is limited. Thermochemical ways show the pyrolysis of biomass hydrocarbon compounds into synthesis gas, carbon monoxide, and hydrogen. And in the reaction of carbon monoxide and hydrogen dioxide is the produced hydrogen. In thermochemical process, a supercritical water, conventional gasification, and pyrolysis method. In biological processes, direct biophotolysis, indirect biophotolysis, photofermentation, conversion of water to gas by biological means, and dark fermentation methods can be counted. Supercritical water gasification. Supercritical water gasification uses the dissolving ability of supercritical water to dissolve various organic substances in biomass to produce high density, low viscosity liquid, which could be quickly vaporized under high temperature and high pressure conditions to produce mixed gas rich in hydrogen. Compared with other biomass thermochemical hydrogen production technologies, supercritical water gasification has unique advantages. Without a high energy consuming drying process, it can directly gasify wet organisms with high water content and will not cause the secondary pollution. In addition, the heat from the produced high pressure hydrogen can be directly used for the combustion engines or turbines to obtain electricity. Although supercritical water gasification is a promising biomass fuel conversion technology, but the application of this technology on an industrial scale still has some limitations. On the one hand, currently only a few researchers have the opportunity to use short residence time continuous low tip reactors or continuous stirred tank reactors for supercritical water gasification experiments. On the other hand, the current research hotspots on supercritical water gasification hydrogen production technology mainly focus on the influence of different types of biomass compounds on the hydrogen production yield. Since the carbon dioxide that comes out as a result of the burning or organic materials produced was previously taken from the atmosphere during the formation of these materials, the environment will be protected in terms of carbon dioxide emissions during the production of energy from biomass. Evaluation of phases containing organic matter is important in terms of environmental pollution and clean energy production. For this purpose, especially in developing countries, the most common source is biomass. Approximately 15% of world energy consumption and 43% of energy consumption in developing countries are provided from biomass. Bence bu gerçekten hani büyük bir miktar. Türkiye'de bu kadar çok olduğunu ben de düşünmüyorum. Hani dünyada gerçekten büyük bir miktarmış. Hatta o gün şeyin çıkışında da konuşmuştuk, gezinin çıkışında. Hani buranın enerji ihtiyacı da biomass'ten karşılanabilir mi diye. Gerçekten öyle bir şey olursa çok bence mantıklı ve iyi bir şey olmuş olur. Energy source of green hydrogen production, wind power. The hydrogen production project by wind power was first proposed by the United States, which produced hydrogen through a generator connected to an electrolysis reactor. The National Renewable Energy Laboratory in the US and Excel Energy have launched by the wind to hydrogen demonstration project in 2004, which uses wind power and photovoltaic power to produce and store hydrogen, maximizing the use of renewable energy and optimizing the energy transfer. After the US, Japan also proposed a series of plans and applications for hydrogen production from wind power. Green hydrogen is produced using renewable energy in this project. In recent years, there are a lot of theoretical and technical research of hydrogen production technology by wind power generation. Some examples: coordinated control method is developed for hydrogen production technology by wind power generation, in which variable speeds wind turbines and hydrogen production devices are installed together. The power curve is smoothed to reduce the impact of the wind energy fluctuations on the power system and hydrogen production equipment. After that, the system is introduced and simulated in detail, and its performance is evaluated. It was analyzed in the influence of the operating temperature of the electrolyzer on the hydrogen production system in wind power generation. The production efficiency at the actual working temperature is compared with the production efficiency at the rated temperature, and the result shows that the hydrogen production efficiency at the actual temperature is overestimated. It was simulated a wind power plant for hydrogen production by electrolyzers and proposed two methods for optimizing the total power of hydrogen production by wind power. It was studied the coupled operation of electrolyzer and wind turbines and compared the operating performance of four types of electrolyzer. Bundan daha fazla çalışma vardı aslında ama hem onların sonuçları hem nasıl yapıldıklarıyla alakalı bilgi vermek biraz uzun olacaktı. Hem de bu çalışmalar aslında yani 2000 yılından 2022 yılına kadar yapılmış çalışmalar. Şu anda hala devam eden bundan daha fazla çalışma var ama daha sonuç alınmamış. Wind power is one of the ways of green hydrogen production technology. Wind energy is converted into electrical energy through wind generators, and then the hydrogen is produced by electrolysis of water and passed through the hydrogen transmission system to achieve the terminal elimination therapy, completing the wind energy converting to the hydrogen energy. According to the way of connecting to grid, hydrogen production technology can be divided into three types. The grid connection system is the way to connect wind turbines to the grid, obtain electricity from the grid, and produce hydrogen by electrolyzing water. This method is mainly used for wind consumption and energy storage of the large-scale wind site, and routes shown in the figure 4. For off-grid system, the electrical energy is produced by a single fan or multiple fans, which is directly provided to the electrolysis equipment without going through the grid or hydrogen production. The grid connected without transmission system is the way to connect the wind turbines with the grid, but the electricity not transmit to other sites, only meet the demand for hydrogen production locally. Energy source of green hydrogen production, wind power, table 3. Table 3, the economic data of hydrogen production by use of wind power as the energy source. The survey from different countries could see that it's economically feasible to use wind energy to generate hydrogen at a certain degree. Solar energy. The solar hydrogen production system by photovoltaic water electrolyzers can be divided into direct coupling and indirect connection according to the connection mode between the solar photovoltaic panel and the water electrolyzer cell. The direct coupling system is through the optimal structure matching between the photovoltaic array and the water electrolyzer without the maximum power point tracking controller, direct current controller, and storage battery, etc., making the system more economical and efficient. Indirect connection is the method used by most photovoltaic water electrolyzers hydrogen production system, which is composed of photovoltaic modules, control modules, batteries, and hydrogen energy storage system. Because the system requires electronic equipment such as MPPT and DC-DC controllers, so not only increasing the system cost, but also inability to produce power transmission loss and reducing system efficiency. To conclude, in terms of carbon sources, although the technology of producing hydrogen from biomass meets the standards of green hydrogen, it still needs to be improved in accordance with the current carbon footprint calculation of the hydrogen production process, so as to achieve carbon-free energy consumption in the hydrogen production process. You can see the economic data of hydrogen production by use of photovoltaic as the energy source, and their efficiency also, and their costs. Conclusion. In the current global energy strategy, the green hydrogen industry is crucial in the development of low-carbon energy. The cost of hydrogen production from traditional fossil energy will gradually rise with the increase of carbon tax and discouragement of the carbon emissions, while the cost of green hydrogen obtained from renewable energy will also gradually decrease with the improvement of technology and the industry in this side. At present, the most promising hydrogen production technology involves the electrolysis of water. In addition, hydrogen production fueled by renewable energy, wind and solar energy, and biomass are also potential approaches in the zero carbon pathway.
Review on the production and utilization of green ammonia as an alternate fuel in dual-fuel compression ignition engines. Prospects for hydrogen, a carbonless fuel face limitations in developing the necessary infrastructure as well as challenges associated with its storage and distribution. Ammonia has been identified as a potential facilitator for a well-established carbon-neutral economy and can also serve as a hydrogen energy carrier thanks to its higher gravimetric hydrogen density. This article provides a detailed literature review highlighting the challenges and strategies for using ammonia as a fuel for compression ignition engines in dual-fuel combustion mode with secondary fuels such as diesel, dimethyl ether, kerosene, hydrogen, and other alternative fuels. Introduction. Hydrogen has been recognized as one of the most promising clean energy carriers that are sustainable and have the potential to contribute to the decarbonization of the automotive and power generation industries. However, the direct use of hydrogen as a transportation fuel faces several safety and storage challenges due to its physiochemical properties such as its boiling point and flammability range. The high-pressure storage method using pressurized gas cylinders is the widely adopted storage technique, whereas in pressurized gas storage systems, improving the volumetric storage density by increasing the pressure is limited by the reduction in pressure. The main disadvantage of the high-pressure hydrogen storage method include low volumetric energy density, diffusion causing leakage, and cylinder stability issues. Liquid hydrogen storage systems use cryogenic tanks are an alternative technique for storing hydrogen under ambient pressure conditions, but the low energy efficiency of the liquefaction process and boiling of hydrogen from cryogenic containers limit the application of this storage method. The difficulties associated with the storage and transportation of hydrogen due to its low density can be overcome using hydrogen energy carriers such as ammonia and brown gas, whose indirect use is highly energy efficient compared to liquid or compressed hydrogen at high pressure. Ammonia is a carbonless fuel with a hydrogen content of 17.6% by weight and can be stored at 25 degrees. Ammonia also has an established production and distribution network as it is widely used in agriculture and industrial applications. Chemical conversion techniques to produce hydrogen fuel from ammonia have limitations in efficiency and economy compared to direct ammonia combustion. A major challenge in the development and optimization of the automotive ammonia fuel cycle is the limited data available on the performance of the ammonia-fueled engines. A few studies have explored the possibility of introducing pure ammonia fuel into an engine. Ammonia green hydrogen carrier. The isolation of gaseous ammonia was first done in 1774 by Joseph Priestley. Frank and Caro discovered the cyanamide process for ammonia synthesis in 1898, wherein nitrogen fixation is effectively accomplished using calcium carbide and formed calcium cyanamide. However, the higher energy requirements for the cyanamide process have limited its applicability on a commercial scale. First, Haber carried out the synthesis of ammonia from its elements in 1908. Resulting is one of the important discoveries that formed the basis of the modern ammonia industry and was awarded the Nobel Prize in Chemistry for this discovery. Haber's patents rights were acquired by BASF Chemicals and the first ammonia plant based on the Haber-Bosch process started operating in Assoc, Germany on September 9, 1913. The process involved the production of ammonia from conventional and renewable energy sources are shown in diagram. 70% global ammonia production follows the Haber-Bosch process, where hydrogen and nitrogen occur in the exothermic process. For the Haber-Bosch process, hydrogen is produced using methane, steam preforming, or water-based electrolysis. The carbon footprint through the steam methane preforming of the Haber-Bosch process showed that for every ton of ammonia produced, 2.16 tons of carbon dioxide is released. Water electrolyzers using renewable energy sources will enable the production of green ammonia as methane-based systems cause carbon emissions. Solid-state ammonia synthesis is an alternative energy efficient method for ammonia production that uses an electrochemical process that uses nitrogen, water, and electricity to produce ammonia. The energy consumed is SSAS process is approximately 16% of Hybride process. Green ammonia production.
Aytucuğum 9 dakika var. 9 dakikada yetiştirebiliyorsan. Yetiştiremezsen kapanırsa tekrar link atacağım. Onu söyleyeyim. Olur mu?
Tamam. Tamam hocam olur.
Sen devam et. Kapanırsa haberiniz olsun. Tekrar link atacağım.
Tamam hocam. Green ammonia production techno-economic feasibility. Ammonia can be classified into 3 types: brown ammonia, blue ammonia, and green ammonia, according to synthesis process and carbon footprint. Ammonia synthesized using carbon-based raw materials such as methane, naphtha, and coal is called brown ammonia, and blue ammonia refers to those synthesized using similar raw materials, but with a lower carbon footprint compared to brown ammonia with the help of suitable carbon. Ammonia synthesized by following a carbon-free route is called green ammonia with zero carbon footprint, using renewable energy sources for water electrolysis, electrochemical reduction, or photocatalytic reduction. Technological readiness level for green ammonia production are of great concern as the commercial applications must address the challenge faced by these techniques. The synthesis of green ammonia based on water electrolysis is considered the most suitable route due to the level of technology readiness and feasibility for short-term application. Some of the key drivers and risks involved in the large-scale implementation of green ammonia production and use are addressed from economic, technical, and political aspects. Some of the green ammonia synthesis techniques with reasonable technology readiness level include electrolysis and biomass gasification, while other techniques in the early stage of demonstration and development are shown in figure. Application in internal combustion engines. Ammonia was identified as a potential fuel between hydrogen, hydrazine, and hydrogen peroxide, considering its properties, use, and storage. Some positive properties of ammonia as a potential fuel for IC engines are detailed in figure. Its injection as a liquid fuel as a higher amount of energy is consumed for the operation of ammonia. Research on the use of ammonia as a fuel in internal combustion engines was carried out in 2 stages for different purposes. The first phase of the research was conducted from the 1960s to the 1970s after the Second World War with the goal of meeting the oil crisis and logistic issues. In the second phase of ammonia fuel research, we started in this new millennium. The main goal was to reduce greenhouse gas emissions through the development of carbon-free fuels. Ammonia's higher octane number and anti-knock properties make it a suitable fuel for spark ignition engines. The presence of ignition source makes it easier to overcome the challenge due to the higher auto-ignition temperature. The extremely low flame rate is an important problem that can be solved using fuel mixture of ammonia and other compounds. Ammonia-fueled compression ignition engines. Engines designed with higher compression ratios were required for successful operation of ammonia-based CI engines, and this justifies the long pause in the literature after the initial phase of research. Some of the possible strategies for using ammonia CI motor fuel include high compression ratio, preheating of the intake air and high compression ratio, dual fuel combustion with hydrocarbon fuels, use of combustion equilibrator. Higher compression ratios are impractical in conventional engines as the allowable compression ratio in real-world application is into 12 ratio 1 to 24 to 1 range. Working only as a single fuel in a compression ignition engine, ammonia is very difficult as it would require very high compression ratio. Successful engine operation with a 95% ammonia fuel fraction was achieved by Ryder and Co. The ammonia fuel shape trend tested by other researchers in previous studies is detailed in the figure. Dual fuel combustion of ammonia. In the literature, it has been observed that the dual fuel approach with secondary fuels such as diesel, dimethyl ether, kerosene, and hydrogen is effective for ammonia combustion. The high autoignition temperature of ammonia necessitates the requirement for combustion in dual fuel mode. With secondary fuels for compression ignition engines, the literature showed that increasing the proportion of ammonia in the fuel mixture reduces carbon emissions but has a detrimental effect on engine performance due to its lower energy density and calorific volume of ammonia. Future research directions include the application of ammonia in advanced compression ignition engines to achieve low temperature combustion mode thanks to their lower emissions, higher thermal efficiency, and fuel flexibility.
Hocam 4 dakika kalmış ama ben başlayayım mı yoksa?
İstersen yeni link atayım, hiç bölünmesin, daha iyi olur.
İyi,
Kapatalım.
tamam.
Bunu ben kaydedeceğim. O sırada hemen yeni linki atarım. Tamam mı? Görüşürüz.
Görüşürüz hocam.